Hello everyone. Today let's begin to learn ultrasonic testing technology together. Firstly, basic physical knowledge necessary for this technology: mechanical vibration and mechanical waves. Our teaching objectives are: 1. Master the meaning of chemical, vibration and mechanical wave. 2. Master the generation conditions and the propagation process of mechanical waves. 3. Be able to use the basic series of mechanical vibration and mechanical waves to explain relevant phenomena in daily life. 4. Be familiar with the application of mechanical vibration in ultrasonic testing. 5. Understand the meaning of the wave equation. Let's start with the first point: mechanical vibration. The mechanical vibration refers to the periodic reciprocating motion of an object near a fixed position. This form of motion is called mechanical vibration, or vibration for short. A mixed position in this definition is a position where a vibration object can remain stationary, often referred to as an equilibrium position. There are many vibration phenomena in our life, such as simple pendulum, piston motion, sound wave, and so on. There are three basic physical parameters that usually describe vibration. 1. Period. It refers to the time required for a vibrating object to complete a full vibration. T, the common unit, is second S. 2. Frequency. The number of times the vibrating object completes full vibration in unit time F, commonly used in Hertz. 3. Amplitude. During vibration, the maximum displacement of the object from the equilibrium position A, commonly used in millimeters. Later, we will use these physical parameters to describe the laws of vibration. First of all, let's look at the types of vibration. According to the force of the vibrating object during the vibration process, vibration can be divided into free vibration and forced vibration. Free vibration means that the object is no longer maintained by external force during the vibration process. It is divided into damped vibration and undamped vibration. Due to the effect of the damped vibration, as the vibration processes, its amplitude gradually decreases until it stops, as shown in the curve 1 in the right figure. On the contrary, the amplitude of the undamped vibration has remained unchanged and has been maintained as shown in the curve 2 in the right figure. Of course, undamped vibration is an ideal situation, and strictly speaking, undamped vibration cannot exist, just as we cannot create a perpetual motion machine. Among them, the simplest and most basic linear undamped free vibration is called simple harmonic vibration, or resonance for short. Obviously, there is no absolute vibration without any constraints, just like there is no absolute freedom in life. Next, we take the spring oscillator as an example to analyze the motion law of resonance. Please observe the spring oscillator animation carefully. From the moment of the spring vibrator, we can find that the vibrator completes the periodic reciprocating motion under the action of the spring force. It shows the following characteristics. 1. The elastic force of the spring always points to the equilibrium position of the vibrator, which we call the restoring force. 2. At the point O of the equilibrium position, the restoring force F equals to O, and the speed V of the vibrator reaches the maximum kinetic energy and minimum potential energy. 3. At the point of maximum distance amplitude A from the equilibrium position, the restoring force F is the largest, and the speed of the vibrator is V equals to O. That is, the kinetic energy is the smallest and the potential energy is the largest. 4. According to the law of conservation of energy, there is mutual conversion between kinetic energy and potential energy in the vibration process. Using the technology of mathematics and physics we have learned, we know that the restoring force F equals to stiffness coefficient K multiplied by the displacement x is also equal to the mass m of the vibrator multiplied by the acceleration a, and the acceleration a is equal to the twice derivative of the displacement with respect to time. From this, the expression of the displacement of oscillator with respect to time can be obtained. X is equal to A cosine open parenthesis omega t plus phi close parenthesis. This is the vibration equation of resonance. In the formula, X represents the displacement of the C oscillator from the equilibrium position, and omega represents the angular frequency of the mass point is equal to 2 pi f. It represents the displacement of a vibrating object at a certain moment during the vibration process. In order to understand well, let's compare the spring moment and uniform circular motion, and then make a clear understanding about the vibration equation, as shown in the figure. The object performs periodic uniform circular motion around the center of the circle, and the center of the circle is the equilibrium position. Obviously, this is also a mechanical vibration. Suppose a circular motion object starts to move from an initial angle phi. After a period of time beta t, The projection of the object's circumferential position in the horizontal direction is the same as the vibration equation just obtained. The vertical projection is y is equal to a sine open parenthesis omega t plus phi close parenthesis. It can be seen that the uniform circular motion can be regarded as the synthesis of the resonance in the horizontal direction and the vertical direction. Following the previous physical knowledge, we know that the period of the spring oscillator is T equals to 2 pi times m/k under the square root. It can be seen that the period of the spring oscillator only depends on the system itself. We call it the natural period, and the corresponding frequency is called the natural frequency. 2. Forced vibration. The vibration generated under the action of periodic external force is called forced vibration, and this periodic external force is called driving force, such as the vibration of the paper cone in the speaker. Let's think about where does the vibration force of the paper cone come from. The basic process is that sound waves are first converted into electrical signals, that is, electrical current. Electricity flows through the wires on the back of the cone. Since the paper cone is in the magnetic field, the energized wire is subjected to the magnetic field force in the magnetic field, which in turn drives the paper cone to vibrate. When the speaker sound wave frequency increases, the cone vibration follows faster. It can be seen that the frequency of the sound wave, the frequency of the current, and the vibration frequency of the paper cone are the same. That is to say, the applied driving force frequency is consistent with the vibration frequency during force vibration. When it is equal to the natural frequency of the vibrating system, it will cause the system to resonate. At this time, the vibration amplitude of the system will reach the maximum, as shown in the figure. In ultrasonic testing, in order to obtain the maximum intensity of the ultrasonic signal, ultrasonic instruments emit not a single frequency, but a frequency range that covers the probe's natural frequency. In this way, due to the resonance, the probe can obtain the maximum electric acoustic energy conversion efficiency and emit the ultrasonic signal with the maximum intensity. This includes the basic theory of mechanical vibration. Now, we move to the second point, mechanical waves. Mechanical wave is a kind of wave which refers to the propagation process of mechanical vibration in elastic medium. From this definition, we can see that the generation of a mechanical wave requires two conditions. One is that there is a wave source for mechanical vibration. The other is that there must be an elastic medium as its propagation medium. Obviously, the propagation mechanical waves is a process, it means that the propagation is the vibration of the wave source. What is an elastic medium? The elastic medium refers to the connection between the particles constituting the material by elastic force, as if there are countless small springs connecting the particles. Please look at the diagram. Each black dot in the figure represents the particles that make up the substance, and the small spring represents the way the elastic force between the particles works. Each particle is bound in its own relative equilibrium position because of the elastic force between the particles. Of course, the elastic force between the particles of different substances is not the same. For example, in a solid material, the elastic force between the particles is relatively strong, so the solid can maintain a relatively stable shape. Liquids and gases cannot maintain a false shape due to the weak elastic force between particles. How do elastic media realize mechanical wave propagation? Take the rope wave as an example. Please look at the rope wave animation carefully. The rope can be regarded as composed of countless particles, and there is an elastic force of interaction between the particles. When the first particle on the rope moves upward due to the elastic force between the particles, it will inevitably drive the second adjacent particle to move upward. By analogy, each subsequent particle will be driven by the adjacent previous particle, and at the same time, it will drive the following particle to follow the movement. This creates medical waves that travel from left to right. So it can be seen that the propagation of mechanical waves has the following characteristics. 1. The motion of each particle in the medium only vibrates near its center position and does not migrate with direction of wave propagation. 2. The vibration of the latter particle always repeats the vibration form of the previous particle, but the time lags behind. 3. The vibration of each particle belongs to forced vibration, and its vibration period is equal to the vibration period of the wave source. 4. The wave propagation process is accompanied by the propagation of force, energy, and vibration, and the particles have driving, hysteresis, and repeatability. When describing the laws of mechanical waves, we usually use the following 3 physical parameters. 1. Wavelength. The distance between the 2 adjacent particles with the same vibration phase on the same waveline is called the wavelength, that is to say, the length of a wave, and this represented by the symbol lambda. Commonly, units for wavelengths are millimeters or meters, as the picture shows. 2. Frequency. The number of complete waves that fluctuate through a certain position per unit time, called the fluctuation frequency, and is also the number of vibrations of the particle per unit time, represented by the symbol F. Common unit of frequency is Hertz, which is times splash second, as the picture shows. 3. Wave speed. In the process of fluctuation, the distance traveled by a certain vibration stays, that is to say, vibration phase, per unit time is called wave speed, which is represented by a lowercase letter c, and its common unit is m/s. Obviously, the relationship between the three physical parameters is wavelength, wave speed c multiplied by period t or divided by frequency f. Through the previous analysis, now we can easily get the equation of fluctuation. Y is equal to A cosine omega open parenthesis t minus x/c close parenthesis. In the formula, y represents the displacement of the particle from the equilibrium position. Omega represents the angular frequency of the particle is equal to 2 pi f. And x represents the distance between the particle and the wave source. Therefore, the wave equation reflects the vibration state of any particle at any time, as the picture shows. Through today's study, I believe that students have a basic understanding of mechanical vibration and mechanical waves. If you want to accurately understand their laws, especially the propagation process of mechanical waves, please continue exploring, thinking and summarizing, and finish homework for practice. Well, that's all for today. See you next time.